have Jason Lee, who's been at the forefront of a lot of the optimization results lately. And today and tomorrow, right? Today and tomorrow he'll be telling us about a variety of things.
Okay, yeah, so today and tomorrow I'm going to talk about mostly about optimization and over-parametrization in the context of neural networks. Okay, so roughly speaking today, we're probably going to get to 1 and 2 today. The slides for 3 and 4 don't completely exist yet, so we probably won't get there. So the first thing I'll talk about is what is over-parametrization. We use this term a lot, like what is an over-parametrized network, how you can modify architectures to make them more amenable to optimization, in particular to gradient-based optimization. Then I'll talk about these more geometric results on over-parametrization. I'll start off by reviewing what kind of non-convex problems are easy that can be solved just purely because they have certain geometric properties. And then I'll move on to certain non-algorithmic results that are kind of suggestive in nature. That kind of suggests that although deep learning is non-convex, the loss function is non-convex, but they have no local minima and that kind of results with no direct algorithmic implications, but they are suggestive and point out that over-parametrization is doing something interesting. The plan for tomorrow is talk about algorithmic results, in particular this line of work using gradient dynamics near the initialization, and then perhaps, if we have time, talk about a Wasserstein flow viewpoint of gradient descent. So 2 different viewpoints. One is kind of local and one is global. But that's for tomorrow. Okay. So today, the goal for these 2 days is to look at optimization and over-parametrization. It's essentially a survey of results, and then some of it with my own perspectives and opinions of how to interpret these results, because the literature is vast. I haven't read every paper, but I've kind of grouped the papers in my head in a way, and then I'm going to explain like this grouping essentially. Okay, so what is over-parametrization? What does this term even mean? Okay, so before we go on, let's look at what's hard about deep learning. Why do we need to look at over-parametrized neural networks? The first thing that's difficult is roughly you can split it into 2 halves. One is optimization. So this is purely the problem of trying to minimize a non-convex loss. For example, the logistic regression loss where your predictor is a network, or the square loss when the predictor is a network. These are non-convex in the parameters of the network. And in fact, due to symmetries, they have many, many critical points. They probably have many, many local minima and so forth. And of course, the second half is statistical, is not only do we care about minimizing the loss, but we care about doing well on unseen data. I won't really focus much on this except to talk about how it's related to over-parametrization. So of course, these are intertwined and they're not easily decoupled. For example, it's not too hard to get the optimization error to 0, but then you might be terribly overfitting and so forth. It's easy to talk about there exist networks that have good test error, but you can't find them with local search. So the question is, the main challenge is how to find a network efficiently using local search that also generalizes well. I won't get to this today, but tomorrow I'll talk about how this recent line of work using neural tangent kernels can get the optimization error very low and kind of get something reasonable for the statistical error. Perhaps not super good, but at least it's not, you're getting some generalization. Okay, so they're intertwined, but I'm going to try and break, today I'm only going to talk about optimization essentially. Okay, so of course in non-convex optimization it should be hard. But practically speaking, if I ran stochastic gradient on all the common networks, ResNet 50, whatever, VGG, you would find that the training loss is very small. The training error is like 0. The training loss itself is near 0, like 0.01. And this is somewhat surprising, right? initializing at random. My algorithm is completely naive. It only sees gradients or subgradients, and it's just following these negative gradients, and somehow it never gets stuck. This is somewhat amazing. That if you contrast this to what you would theoretically expect, on the theoretical side, everything is hard. For example, you can try to fit a loss function with a single neuron and a sigmoid activation, and when the data is not realizable, the loss function has a lot of critical points, exponentially many local minima. That was shown a long time ago in this paper here. And there's many other hardness results that suggest that you should not be able to learn these. For example, it's known that even if your data set is separable by logarithmically many, super logarithmically many ReLUs, so you have a teacher network that consists of ReLUs, k-ReLUs, and they separate with positive margin, you should not be able to learn in polynomial in the number of ReLUs you have. That's what these results kind of suggest. Okay. So the main question of this tutorial is to understand why stochastic gradient is successful, why on these terribly non-convex problems it can still minimize the training loss. Notice the second one is the hardness is about learning, so it doesn't preclude getting the training loss to 0 necessarily. But the first one does say that even when my loss function has 1 neuron, the training loss is bad already. Okay. Let me define my setting. So I'm going to, this is my loss function. I may or may not have a regularizer. The loss will be either square loss or logistic loss, and potentially like a hinge loss or a smooth hinge loss. But it's a univariate function. It's convex in the argument y hat. Okay. The network is denoted f theta at x. So it's what the neural net predicts at x. I'm only going to look at scalar outputs. And theta will denote all the parameters of the network, so all the weights. And we're only going to look at one algorithm, gradient descent, or SGD, is you simply move theta in the direction of the negative loss. Okay. So some more notation is, so the set of all parameters, I'll denote theta. The weight of individual layers, I'm going to denote W sub L. And I'll sometimes treat the output layer in a special manner. I'll call it A. So A is a vector because I have scalar output. And W sub L are matrices of size m by m. I'll use square for convenience. M is the number of filters, number of neurons per layer. The input is going to be in D dimensions. The width is always m, and the depth is L. Okay, so the total number of parameters, so if you take all the W's and the A's and concatenate them, I'll call that P. And there's going to be n samples. So the goal of optimization is to minimize the following training loss, right? I want this to be 0. If it's square loss, if it's logistic loss, I want it to be very close to 0. Okay, so now I'm going to talk about what is over-parametrization and why do we need it. Okay. So like I already told you, even in the single neuron case, when the data is not realizable, or it's not realizable plus noise, there's exponentially many local minimum. So obviously, gradient descent is going to get stuck if you commit to using that loss, right? Of course, the goal of machine learning is not to do optimization. Optimization is simply, a way to try and learn a good classifier. So we don't commit to using that loss function. If I'm doing not only optimization, I'm dead. Like if your goal is to minimize the loss, that's hard. But we're doing learning, so we can change the loss function. What is the simplest way to change the loss function? It's to alter the model, to alter the architecture, right? So even if my model came from a realizable single neuron with plus some weird noise to make it hard, I can always decide, okay, I'm going to fit a different model. And then with this different model, I may be able to get the training loss to 0 more easily using stochastic gradient. Okay. Just for example, it might have the property there's no bad local minimizers, or perhaps it has the property that there's a solution near random initialization. Meaning you randomly initialize and you're in the Bayesian of attraction of a minimizer. Okay, so basically you're going to change the model to make the loss landscape look better. This is some illustration. It's not very good because I don't think this is, I'm not saying this is what the losses look like. But the point is here, it'll succeed, and on the left, it'll fail terribly. Okay. So what is the simplest way to change the architecture or change the model I fit? One very simple way is to just over-parametrize. For example, if I, for some reason, believe that the data is fittable by this small network with 50 neurons, I can decide to use a model with 100 neurons, right? And then it's empirically observed that it's easier, somehow it's easier for SGD. The training loss is nicer when you use 100 neurons rather than 50. Right? With 50 neurons, you frequently get stuck in crappy local minimizers or the gradient vanishes, whatever. And with 100, you do well. So here's an experiment showing this. What I did is I generated data from this 2-layer model in 50 dimensions, and there's 50 neurons. The weight matrix is just identity. So the simplest weight matrix in the world. And then my labels Y come from this true teacher network. So it's completely realizable. And then my model is also this teacher network. I run SGD 5 times, and then I plot the loss value. So you can see that I'm getting 2 different unique values of the loss, and neither of them are 0. The global minimum is 0. I mean, I know that there exists a model with 50 neurons that gets 0 error, namely W star, which was the identity matrix. But SGD can never find it. I mean, you can run it instead of 5 times, you run it 50 times, it still doesn't find it. And in 50 dimensions, you'll never find this if you just use SGD. Okay. So clearly, the loss landscape is not good, right? And this is kind of not surprising. You know, you're in 50 dimensions doing non-convex optimization. Of course, you would expect that you very rarely find the global minimizer. And in fact, you should get very different quality local minimizers depending on your initialization, your learning rate schedule, so forth. Okay. On the right-hand side, my data generating distribution is the same thing. My data still comes from this small teacher network with 50 neurons. But I decided to use a different model. I don't know why, but I decided that I want to use a model with 100 neurons now. Of course, this seems statistically silly. I know the true model had only 50 neurons. Why am I wasting all these parameters, potentially losing statistical efficiency, increasing my computation time? I mean, there's a lot of drawbacks here for sure. But magically, I call SGD 5 times with different initializations, different data. I mean, it's stochastic data. The data is coming in stochastically. This is 1 pass SGD. And the objective, the training loss value, or actually this is populations, 1 pass SGD. So the population loss is now going to 0. Okay, and it doesn't matter where I initialize. You can see that it's getting a global min or very, very close to global min, something like 0.01 in the training loss. Okay, so this is kind of surprising, right? I knew my model was well specified, and I decided to fit a big architecture to make it misspecified. But now the optimization algorithm is working. From the perspective of optimization, I've somehow magically made the training landscape very good, or even the population loss very good, more amenable to SGD. Any questions before I continue?
The weights it converges to, how different are they in different runs, and how different
very
are
different
they from the true one?
They're not the true weights. They're very different, but they have population loss 0, near 0, yeah. I mean, there's some patterns. Like you can see, like Sometimes you capture a little bit of the identity, but I didn't see any, nothing stood out, I guess. Yeah.
Is there a phase transition as you go between 50 and 100, where all of a sudden?
Yeah, something like around 55 it didn't work, and then 70 it started working, and then I just made it 100. So there's a phase transition. Ohad and his student have a paper that empirically looked at this a little bit, and they found when your true model was 20 neurons and you use 21, it still gets stuck. And if you use 22, it didn't get stuck. So, I mean, no one knows. And this is an interesting theoretical question. Like, you would conjecture maybe if you had k neurons here, something like k log k, it would work. I think it's true. No one can prove it. That would be one open problem.
Is this just Gaussian data distribution?
Yeah, the x's are Gaussian.
So there's single Gaussian.
Yeah. Yeah, the x's are standard normal in an IID. Okay. Yeah, so there's some phase transition, but I have no idea where it is. Okay. So sort of this summarizes this conventional wisdom on what over-parametrization is doing. Yeah, Renee.
The question of the data is important from the following perspective. You have a classifier at the end, so if the input was a mixture of two Gaussians, you might be learning a classifier, but if you just have the input that comes from a single Gaussian, then what is the second layer?
It's regression.
Just regression.
This is regression. Yeah.
And how do you generate the weights for the second?
Also plus minus 1 at random.
Right.
Yeah. Okay. So kind of this is the rule of thumb, is if your SGD is not finding low training error, then you should make your model bigger. And then somehow by throwing in a bigger model, SGD is more likely to get low training error. And kind of we see this happen all the time in practice, is that the models are fairly big. When we get bigger data sets also, we use bigger models. So of course, one theoretical problem to ask is how much over-parameterized do you need to optimize? And what does it mean for the test error, right? Just purely computationally, throwing in more parameters increases computational and memory cost. I mean, optimizing 1 billion parameters is not easy. And naively, you may think that too many parameters may lead to overfitting. For example, when I increased this, I doubled the number of parameters roughly. And of course, you would think to learn this model with twice as many parameters may need twice as many samples. So clearly, if you can minimize over all models with 50 neurons, and you had another oracle here, this one might be statistically more efficient.
One more question about the experiments.
Yes.
Are the solutions sparse or dense when you use 100 neurons?
Are the solution? What do you mean by sparsity?
For the parameters.
It's a full rank matrix at the end. Sorry, it's 100 by 50, but it's
But when after training,
yes.
are the parameters still dense, or are they most of them is a sparse solution that you get?
No, they're dense. There's no structure popping out. Yeah. Okay, yeah. So you may think that also you're making optimization easier, but perhaps you're making statistics harder. This is also a possibility. So then you want to kind of find a sweet spot, or this phase transition, like you mentioned, is that at what point can I efficiently optimize? What is the minimal amount of parameters I need to efficiently optimize? Okay, so obviously if your labels were arbitrary, you would need the number of parameters to be bigger than the sample size. This is just simple dimension counting informally, is that if I have n equations, then I need as many parameters to move around to fit all the equations, right? So I need p bigger than n. So this is like worst case. A more interesting question is if the labels were structured, the x's and y's were structured, can the amount of over-parametrization adapt to this latent structure in the labels? Then obviously you wouldn't need this worst case anymore. Okay, so kind of a taxonomy of the results on over-parametrization. The first category of results are mostly geometry or topology based. They're kind of non-algorithmic. They say things like all local minima are global, or all strict local minima are global, or some variation of this. This is the first category of results. The second category of results are based on these local dynamics. They've been referred to as the lazy regime or the kernel regime. And they utilize the local linear behavior of the network predictions. What's surprising here is using a purely local analysis, you can argue you get a global optimum. The third category of results is these more global dynamics or active training, or I don't know what the right term is. They're kind of characterized by the parameters moving a lot from the initialization. The parameters are kind of forgetting where they start. OK, so for today, I think I will probably be covering the first one and maybe a little bit of the second one. All right. Oh, yeah. And before I go on, I want to talk about one more architecture design concept, basically skip connections. So over-parametrization is increasing the width. And this is very useful if you have a shallow network and you want to prevent gradient vanishing. You make the width bigger. Similarly, if you have very deep networks, even if when they're over-parametrized, the gradients may vanish just because you have small numbers being multiplied L times if you're L depth. One simple idea is just to use skip connections or ResNets is to just add these links over here. And that way the gradients, when you take a gradient of a very early layer, they don't disappear. So this is also another type of architecture design that I'll talk about briefly later too. OK. Oh yeah, and it's worth mentioning roughly these have the same expressivity power as a regular network, right? So ResNet is not really increasing the expressivity or anything. It's purely to make optimization easier in a sense. I don't know what it does to the statistical error, but it definitely isn't making it more expressive anyway, right? You can basically express the same class of functions here and here. Basically, at the widths we're talking about, you can express all functions informally. But this is just a way to reparametrize so that stochastic gradient is less likely to get stuck. OK. So let's move on to these geometric results on over-parametrization. I'm going to start off by reviewing generic non-convex optimization. And then I'll go on to specific results in deep learning. OK. So sort of these geometry results, they roughly have two steps. In the first step, you say something about gradient-based or local search algorithms. For example, we know generically that stochastic gradient or gradient descent will always find a first order stationary point somewhere where the gradient is 0. Or with a little bit more work, you can show they find a second order stationary point. So then we know that no matter what, these algorithms get certain type of critical points. And the second step is to show that these critical points have good properties. Maybe they're global minimizers or close to global minimizers. So you can separate things into two steps. OK, so what is the first step? So even when the function is non-convex, people have identified these numerous things that look like convexity. They go by various names: quasi-convex, one-point convexity, regularity condition, blah, blah, blah. They all basically say the same thing. They say when the gradient vanishes, something good happens. So for example, this condition, which is very similar to quasi-convexity, it says if the gradient inner product with theta minus theta star, which is the direction I want to go to, because I want to move towards theta star, is lower bounded by some distance to optimality, this d of theta, theta star. For example, I just need something positive here, basically, unless I'm optimal. When it's optimal, it can be 0. When I'm non-optimal, I need something strictly positive. For example, if it's bigger than L of theta minus L of theta star, this is sort of like quasi-convexity. And you can see it has the property that unless I'm optimal, then this is strictly positive. And if I take a gradient descent step, I thus move towards theta star. Here's a more fancy version. It goes by various names, but basically it's just a mix of two terms. It's saying that this is the more important term. It's saying that I'm lower bounded. I'm like strongly convex in this one direction. It's saying that there's strong convexity in the direction of theta to theta star. So perhaps I'm not globally strongly convex, or even in the ball, but I'm strongly convex along one direction. And this is the one direction that matters because it's what gradient descent is looking at. And if this holds, you can also prove a convergence rate for gradient descent to theta star. Again, this side is only 0 when you're at the optimum here. Okay, so quasi-convexity is, so this is slightly like epsilon away from convexity, where you can still say that gradient descent is finding a global minimizer. Okay, so I'll call all of these quasi-convexity or one-point convexity. People have used this in some simplified neural net settings. They essentially all look like this, where this is something quantitative, and it's different for every paper. Okay, the simplest one is where you have one neuron. Okay, so it's realizable. Y is ReLU of Wx, sigmoid of Wx. It really doesn't matter. I think it just needs to be convex or monotone. Either convex or monotone will work. For example, in this Wertinger flow paper, it was a square function or quadratic function, basically phase retrieval. In these functions, it was like sigmoid or some monotone function. And then in these ones, this was like a ReLU here. In all of these, it has this kind of geometric property that the gradient points in the right direction. Similarly, for when you have a single convolutional filter with non-overlapping patches, so this is a shift operation, and they don't overlap, then it also has this property as shown by Brutskis and Globerson first. You also have this one-point convexity in a neighborhood around the identity. This, in these papers by Li and Yuan, basically they wrote it as a ResNet, but what it boils down to is if W star is the identity, then there's a radius of constant spectral norm, roughly less than 0.07, such that it has one-point convexity. So if you started in if your W star was close to identity and you start within a constant spectral norm, then gradient descent converges to W star. And also shown for linear dynamical systems in this paper by Hart, Ma, and Recht, they showed that a form of this one-point convexity. Okay.
So in the second to last bullet, so W star is the W's in the first layer?
W is the hidden layer weight.
And the top layer is just the sum and the output?
Yes, the second layer had to be all positive.
But I see, so it's a sum?
It's a sum, yeah, that's right. And so a small spectral norm radius around W star, but only for W star near identity. So, yeah. Okay, so this is sort of kind of the easiest way to prove something is you only use a gradient. Using only first order conditions, although it's non-convex, you can say something. And you can see, I mean, it's pretty limited, the list here. Very simple neural nets. Essentially one neuron models. Okay. In over-parametrized networks, it's kind of inconvenient to be talking about theta star, right? Because if it's over-parametrized, theta star is not identifiable. So the theta star you go to may depend on where you start, your learning rate, so forth. So so what's frequently used is this Polyak gradient domination condition. Sorry, there's a typo. This should be squared. In this gradient domination condition, I don't need to know what theta star is. I only need to know what L of theta star is. Throughout today, L of theta star will always be 0. I'm assuming I can fit the data. So it just says that the gradient doesn't vanish. As long as my loss is not at the global optimum, my gradient is something positive. And gradient descent always makes progress proportional to the square of the gradient. So then you always make progress if you have this gradient domination condition. So it's basically immediate to prove that if this were true, then gradient descent gets a global optimum at a linear convergence rate. Okay, so when does this hold? This condition is useful for over-parametrized models, basically. This condition holds for locally near a small radius in Frobenius norm for over-parametrized models. And it holds globally for, it also holds globally for over-parametrized models, assuming you initialize in a, using Xavier, using a like Lacoon initialization, essentially. I'll talk about this later today or tomorrow. And interestingly, in ResNets, it satisfies the Polyak condition, this Polyak gradient condition, in some large region around initialization. And this is something you get from using linear ResNets instead of linear networks. Sorry, was there?
Why does the gradient domination condition depend on the initialization? Isn't it a property of the function itself?
It doesn't. I'm saying that if you wanted to use this one, it may. Because if you're over-parametrized, theta star is like the global min you go to. But which one are you going to? You don't know, right? Yeah. Okay, so this is also, again, a first order condition that's useful in the over-parametrized case to get global convergence to a global minimum for gradient descent. Okay. So of course, what these two have in common is you want to avoid spurious gradient vanishing. The one thing that kills gradient descent is the gradient is 0 or near 0, but you're not yet at the global minimum. That's what both of these are ensuring. This is saying the norm squared of the gradient is lower bounded. This one's saying the gradient in a particular direction is lower bounded. They kind of, morally, they're the same thing. The gradient doesn't vanish unless I'm at a global optimum or somehow close to it. Okay. So what if the gradient is 0 then? Are we dead? Okay. So let's look at Taylor's theorem. So just apply Taylor's theorem to the loss. And let's say the gradient term, the first order term is 0 or it's nearly 0. It's so small, it's not going to help you. Okay, so what to do here? We're still okay if theta minus theta 0 is aligned with a negative eigenvector of the Hessian, right, at theta 0. So when the first order term is 0, it goes away. If I can make this negative, then I'm safe. I can still decrease the loss, right? Okay. So what is an obvious algorithm that can use this to avoid gradient vanishing and Hessian vanishing? So here is an algorithm by Royer and Wright. It's probably older than that, I think. It's very simple. You just run gradient descent until your gradient is like 0. Then you compute the negative eigenvector. If the negative eigenvalue is not 0, or sorry, is away from 0, you move in the direction, you let dk be a negative eigenvector, and you move in that direction. And then you loop again. When the gradient, you keep running gradient descent until the gradient is 0, and then you try to escape. Okay. So it's pretty obvious that this algorithm is going to succeed in finding a place where the gradient is roughly 0 and the Hessian is positive semi-definite. Why is this? Let's say the gradient is not 0, then the gradient descent step is moving, right? This step, the first phase of the algorithm, is making progress. If the Hessian is not PSD, then there is a negative eigenvector, and it's going to move in that direction here. Okay, so when this algorithm does terminate, according to these tolerances, whatever it is, here and here, then it'll find a point where this is less than epsilon and this is bigger than minus epsilon. Okay. So if theta satisfies the above two conditions, we'll call it a second order stationary point. So reasonable algorithms that use second order information can find second order stationary point. This algorithm here has some running time that's polynomial and everything. Okay. Okay. So here's just a picture. these points are the ones we're getting out of using the negative curvature. If I'm exactly here, then the gradient is 0, but the eigenvector computation is going to see this direction and move it off this kind of point. This kind of point we don't worry about. At the end, we're going to get a local min like here. Okay, so very informally speaking, a second order stationary point is sort of like a local min. Okay, so of course, I showed you the algorithm for escaping second order when there's second order negative curvature. There's an obvious way to generalize this algorithm is you run gradient descent until the gradient's 0, then you take a step in the negative eigenvalue. If that's 0, then you try to use a third order tensor, find negative curvature there, and you keep going higher and higher. And this algorithm will work. Unfortunately, computing these negative curvature directions becomes hard at fourth order. So third order saddle points can be escaped by essentially an algorithm that tries to find third order negative curvature. But as soon as you go to fourth order saddle points, it's hard. You can reduce copositivity testing to fourth order saddle points. This is kind of bad news. Generically speaking, neural nets of depth L will have saddles of order L. For example, even a linear network has a saddle of order L, just because x to the lth power is a saddle of order L. So in summary, let me just make a remark that second order stationary points with equality constraints is the same algorithm. But as soon as you have constrained optimization, it's NP hard. You can, yeah.
But the achievability statements will never promise that you will find these points in polynomial number of iterations, right? So the hardness is fine, but I'm saying you will always make progress, but will you reach this local minima in polynomial time? So the third order cells can be escaped, but...
Yes. Oh, you will, yes. You make sufficient descent.
Okay.
Yeah, the hardness is if you could compute arbitrary order tensor eigenvalues, then an algorithm that looks like this will make sufficient progress every step. The hardness is finding these negative curvatures at fourth and higher order.
Okay.
Yeah. So for third order, if there is a negative direction, you can always find it. You don't need any assumption on the tensor.
You don't need any assumption on the tensor. It's not really computing a tensor eigenvalue in this paper, I think. It was doing some random projection thing, and then it showed that with like some small number of projections, it can find it. I think that was roughly that. Yeah. There was one more.
Is it necessary to explicitly compute a negative curvature direction? Or
no, it's not.
No. Just like randomly perturb the parameters, right?
That's next slide. Yeah,
awesome.
You're one slide ahead of me. Yeah. Okay. Yes. So. Yeah. So. Okay. So on the previous prototype typical algorithm used second order information. The obvious question now is, frequently Hessian vector products are expensive in PyTorch TensorFlow, so forth. If we have no access to the Hessian, can we also avoid saddle points? So naively, you might think this is difficult because, if the gradient is 0, gradient descent should be stuck, right? It doesn't really see the Hessian at all. Okay. But this is where randomness comes in. Let's look at a small toy calculation. Imagine that theta 0 is 0, and 0 is a critical point. The gradient is exactly 0. And we run GD from a small, infinitely small perturbation of 0. The iterates will roughly look like this. It'll look like identity minus a step size of the Hessian raised to the tth power. And notice this is seeing second order information. The gradient term is gone because the gradient is 0. So then when you apply identity minus step size times Hessian, what this is doing is power iteration on the Hessian. So at critical points, gradient descent in fact does see second order information because the gradient term is gone. And away from critical points, it sees no second order information because it's dominated by the gradient term. Okay. So how can you use this? Here's a picture that's illustrating the same thing. 0 is my saddle point. If I start anywhere near 0, I'm doing power iteration, and eventually I will escape. I'll go in and I escape like this. So basically, as long as you have some randomness, you'll escape the saddle points. This is just saying the same thing. It's a set of measure 0 that you do get attracted to these saddle points. Okay, so what is the theorem? The formal theorem you can prove is that a function is smooth and coercive. Coercive just means that the gradient blows up as I go to infinity. I don't want a function like e to the minus x, because it has no critical points. Then gradient descent with additional noise or some source of randomness, either stochastic or I inject it artificially, doesn't really matter, only affects the rates. I get a second order stationary point, or epsilon second order stationary. The gradient will be epsilon, and the Hessian will be bigger than minus epsilon. Okay. So what this means is that gradient descent with randomness will find a second order stationary point in polynomial time. Any questions here?
Is this condition necessary here, or just be you to define the?
Yeah, you do need, if you want polynomial time, you need a quantitative bound on the Lipschitz of the Hessian. If you only want it asymptotically, you don't need it. Right. But you need C2 regardless. I don't think you can escape saddle points with just C1. The difficulty of saddle points with just C1 is essentially the same as finding a second order stationary point with constrained optimization. Because with constraints, you create essentially, it's a boundary behavior will kill you. Okay, so just summary is gradient-based algorithms find second order stationary points. Okay, so what this means is that we can now look at a larger class of problems, right? Before I was only using that the gradient is non-vanishing implies global optimality. Now I can say the gradient is non-vanishing or the Hessian is non-negative. So this is, I can look at a larger class of problems than before. This has been done. So these, for a large list of problems now, pretty large list, second order stationary points are almost global minimizers. Matrix completion, rank K approximation. So basically everything here looks like some modification of SVD, or tensor decomposition. So anything that looks like computing an SVD or orthogonal tensor decomposition, the second order stationary points are going to be global minimizers. Okay, so what does this mean for neural networks? I know of 3 examples where neural networks are second order stationary points, and I'll talk about these next.
So for Maxwell, Maxwell is a bit hard, right? So you're talking
this is the
guarantee for, you can only get epsilons, but
it's that if I do the Gomans-Williamson relaxation is an SDP, right? Okay. And then to save memory, instead of solving an SDP, I make it low rank. That problem has the second order stationary points are global mins of the SDP. So you get the same approximation ratio as the SDP.
That's
right. Okay. Okay, let's talk about what is known for neural nets. Well, one obvious idea is that if I have neural nets and the activation is quadratic, it's basically matrix sensing. Okay, so if my true model looks like, if my model looks like this, my data can be anything. My model looks like this, and I minimize square loss or logistic loss, and the number of neurons is bigger than square root n, then all the second order stationary points are global minimizers. This is essentially the same reason that the Burr-Monteiro relaxations work when you have square root n rank. It's kind of the same problem. There's some latent SDP structure here. Okay. With ReLU activation, so this one is more tricky. My true model now comes from a ReLU with strictly positive output layer weights. Okay. W star j can be anything as long as the matrix is full rank. Then I need X to be Gaussian. The output layer weights are positive, and K is less than D because I need it to be full rank. There exists a loss function that's implicitly doing tensor decomposition. Like I can write it down, but it would take up 5 slides. And that's the population one. If I wanted to write down the sample one, it would take like a slide deck to write it. So there's some complicated function that's encoding tensor decomposition. And if you, all second order stationary points of this tensor decomposition loss are a permutation of the global minimizers. They're just going to be permutations of the W star j's.
Jason, is there dependence on the condition number of your weight vectors? For
Yeah, there is. It's polynomial. I don't know what it is, actually. Yeah. Okay, so, yeah.
And won't you get into this non-smooth setting?
No, this is tricky because it's Gaussian, so it smooths it out.
Right, but if you're talking about a sum, that's why I'm saying about if you're looking at stochastic gradient.
You can do either. You can show that if you have enough samples, the non-smooth doesn't hurt you on the training loss. Or you can say I'm doing one pass SGD. Either one will work.
Is it like a full gradient?
Yeah, exactly. The population loss is interesting. It's a mixture of tensor decompositions, which is a smooth thing. Okay. Oh, sorry. I said that wrong. Sorry. What you're saying is if you do gradient descent on the obvious loss function, like square loss, this tensor decomposition loss is smooth, even when the activation is ReLU.
I see.
Yeah. I'm sorry. Okay. So you can, some things are second order stationary points, but if you are not willing to use these really convoluted and weird losses, then it's quite limited. It turns out with one neuron, the gradient was not vanishing. It had these one-point convexity properties. With two neurons and the weights nearly orthogonal, you can show that every second order stationary point is a global minimizer. It's extraordinarily painful high school trigonometry to do this. And it works with 2 neurons, and Ohad's paper shows somewhere around 6 or 7, it starts failing. So this is clearly not true. And the experiment I showed you it's not true at all for 50. Right, so there's no way to make more progress on this. And it's too painful. And also when you have one convolutional filter, non-overlapping patches, it's true. Okay. So we've made a little bit of progress, but not much, using second order stationary points. And all of these results are algorithmic here. So you first prove that epsilon second order stationary points are good. And then you invoke SGD or perturbed gradient, and it finds it in polynomial time. Okay. So now I'm going to move on to non-algorithmic results. Let me take questions first. Okay. So for the non-algorithmic results, we're always going to work in the settings where the parameters is much larger than the sample size. And let me just view everything as a nonlinear least squares or nonlinear logistic regression, but I'll use least squares. It's more convenient. And I'll use a shorthand that Fi of theta is the prediction of the network on sample xi. Okay. So what is the optimality conditions of nonlinear least squares? Let me define a Jacobian matrix with columns the gradient of Fi, right? This is just the Jacobian of f of theta, where you view f as a map from Rp to Rn. It takes parameters and outputs a prediction for every sample. Then there's a Jacobian matrix, which is P by n. So since P is bigger than n, it's a tall matrix. And I'll call the residual or the error be just Fi minus Yi. So it's a vector of length n. So if you just look at you take a gradient of this and set it equal to 0, the optimality condition looks like this. It's some tall Jacobian matrix times the residual equals 0. This is completely obvious, but a powerful observation is that when you have a tall matrix, generally the nth singular value is positive, right? Tall matrices are full rank, column rank, generically speaking. If sigma min of j, sigma n of j, the nth one is positive, times the residual is 0, the only possibility is that the residual is the 0 vector. If the residual is the 0 vector, then this is a global optimum. This loss function is the L2 norm squared of the residuals. Okay, so if I can magically find a critical point with sigma min of j is strictly positive, then I'm optimal. I'm globally optimal. Why is this? I run gradient descent. It gets an epsilon approximate critical point, and then I just do one step, and then the norm of the residual is less than epsilon divided by sigma min of j. As long as this is lower bounded, I'm done. Right? I found the training loss, the L2 training loss is order epsilon. Any questions before I go on?
Is the similar argument called for like general loss function, example L2?
Yes, I have that in one slide. Yeah. Okay. So the only thing to do here is to ensure your optimization algorithm finds a full rank Jacobian. It finds a first order critical point, and the Jacobian is positive, strictly positive. Not positive, strictly minimum singular value is positive. Then it's epsilon global optimum. Okay. Oh yeah, other losses. I was talking about square loss. Essentially the same reasoning holds. You just have to define the residual in a different form. The residual is now the derivative of the loss value. And so again, the residual is less than epsilon over a sigma min. And for all the commonly used losses, the derivative upper bounds a loss because it's convex, right? It's convex in the y hat argument. So if I can make the derivative 0, then the loss must be at the global min. Okay. So this nonlinear least squares analogy does work for any convex loss or even, yeah, basically any loss. Okay, so how to find non-degenerate critical points? Well, the short answer is no one really knows. Here's a more nuanced answer, is you can, of course, say topological things like for almost all theta, the Jacobian is full rank when over-parametrized, right? Like the Jacobian is somehow a function of parameters, but low rank matrices are a measure 0 subset. So as long as this function j of theta is kind of analytic-ish, then almost all critical points are global minima. And this is what a large series of papers are essentially kind of doing under the covers. Okay, so I'll talk about 3 different strategies people have taken to do this. The first strategy by Sodry and Carmen uses some sort of auxiliary randomness, omega. So they modify the problem so that j, the Jacobian, is a function of your parameter theta and some auxiliary randomness omega. So even when your theta depends on the data. So notice the difficulty is all that the way algorithm returns you a theta is it looks at the data. And thus, all of these statements about almost everywhere don't say anything because gradient descent is, of course, returning you something in a measure 0 set. Critical points are measure 0. So the idea of Sodry and Carmen is to inject some extra randomness. It's not completely rigorous. It kind of suggests that SGD with this auxiliary randomness can find a global minimum. I'll kind of describe this in a second. The second strategy is to make a lot of assumptions and somehow pretend that theta is independent. This is this paper of Kawaguchi. They list some assumptions that make no sense to me, but somehow it implies that this Jacobian was independent of things. And then this third one is these purely topological or geometric statements is just say things like almost all critical points are global minimum, where almost all basically says you just can't find a place where the Jacobian's 0. Okay, so kind of they all have the same idea, so I'll kind of describe what I think is the proof idea here. Okay, so remember we're looking to minimize f minus y. The only thing is that f is a neural network, right? The target is very clear. I just want f to go to y. So let's look at a place where f0 is non-optimal. What direction do I want to move f0? Well, if I take a gradient of this, it's very obvious that y minus f is a first order descent direction in the function space. If I view this as objective, it's very clear I just want to move in the f minus y direction. Okay, so the only catch is I need to do this in parameter space. If I'm optimizing in function space, this is completely trivial. But how do I find a parameter that kind of mimics the functional gradient descent or gradient boosting? Okay, so let's look at some f of theta 0, which is f0. For theta 0 to mimic the descent direction, we're going to need to solve an equation like this. Again, it's the Jacobian matrix equals to the direction I want to go in. When this Jacobian is full rank, meaning its nth singular value is strictly positive, I can invert the matrix and find the direction to go in. And then I'm done. I've escaped such kind of points. Okay, so what if the Jacobian is 0? Then you can try to look at the higher order Taylor expansion. Again, f is some function. Its first order term is potentially 0. So informally speaking, you can try to look for second order descent directions. You can try to solve this thing equal to y minus f. And then this will allow you to escape certain second order degeneracies and so forth. You just can keep going up in order, and this will allow you to escape kth order points if you could do this. Since we don't know y minus f, one thing to do is just compute eigenvectors, minimal eigenvectors. So this is informally what's kind of happening is that when the Jacobian is 0, it's exactly when your problem has no first order escape direction. Okay. So you can take this argument to infinite order, and then basically an infinite order stationary point is essentially a local minimizer. So if the mapping is locally onto, meaning that I take a ball around my parameters, and then I apply f to it, and I get an open set in Rn. So geometrically, what I want to be able to do is I want this mapping from parameters. So this is theta 0. I take a little ball here, and then I map it under f. Now I go to parameter space. Sorry, this is prediction space. And I still want to get a ball here, or some open set. If I can get an open set, then I can escape. Because if I can get an open set, I have the direction f minus y here, right? And then if I if my set is this open set, the bad case would be it's like missing a slice. It's like this or something. And then I don't see y minus f, then that's a bad local minimizer. As long as it's an open set here, or onto, then it's not going to be a bad local min. Okay. Of course, it doesn't mean you can find the direction, so this is why it's purely topological. In contrast to these strict saddle or second order stationary points, which allow you to not only say it's onto, but you can find such a direction. Okay, wow, that's dense. Okay, so how is this related to overparametrization? So let's look at two-layer networks. And imagine that the hidden layer is super, super wide. Okay, when the hidden layer is super, super wide, I can always find and W is full rank, then the Jacobian matrix will in fact be full rank. Sorry, let W0 be random, and then the Jacobian matrix will be full rank. Then I can solve an A. I can only use A to find a first order descent direction, right? So this is saying something trivial. It's that if you have n neurons, initialize them at random and fit the output layer. Clearly, you can escape any, any degenerate direction and get to a global min. So the only potential issue is if this matrix sigma of Wx is rank degenerate. This Jacobian here is actually just sigma of Wx. So, okay. So then how do you get out of such directions is that imagine it were a local minimizer where the error is not 0. You just want to make an infinite perturbation to W to make sigma of Wx full rank. Let's say sigma is analytic. And then so almost any perturbation will make that matrix full rank because analytic functions plus rank degenerate means that low rank things are very unlikely, measure 0, if sigma were analytic. And then you make a perturbation to A to move in the direction of y minus f to escape, right? So this is a second order perturbation in a sense. You move W a little bit to ensure the Jacobian's full rank. Then you move A a little bit to go in the direction of f minus y or y minus f. So roughly speaking, there's no spurious local minima. Papers, like the first paper I could find on this was basically this Poston paper that says something like if all hidden layers, if there exists a hidden layer that's very wide, at least n wide, then all local minima are global, roughly speaking. Oh yeah, here it is. So the theorems that look like this say something like, take a network, a feed-forward net that's very deep. You have one layer that's very, very wide. And then all the layers after that are shrinking in width. Then almost all local minimizers are global. There's a second form of such theorem which say that under the same conditions that you're very, very wide, then there exists a path. And the path is non-increasing, meaning you go from theta to theta star, and you don't increase the objective value, the loss value at all. And you can move to theta star. It doesn't mean that SGD will find such a path or anything like that, but it does imply that every strict local minimizer is a global min. Yeah, Peter.
So your argument was about the nonlinearity being analytic. What can you say about the relative case?
I don't know. In fact, this argument is not from these papers. They had some weird proof that I couldn't digest fully. And none of them cover ReLU, I think.
Does work with ReLU? No, it works with ReLU. It requires the function to be positively homogeneous. And so ReLU is one such function.
No, but they don't say all local minimizers are global, right? They have extra conditions if you want ReLU.
Well, it says the second form, basically. You get the non-increasing.
Yeah, sorry. You can get this one, but I don't know if you can get that one, I guess.
This one's
yeah,
not.
that's probably more correct. But I think the ideas are all kind of similar, is that you basically just perturb the parameters, and then you can, if one layer is very wide, you can use the outputs. Imagine the very wide layers at the very end for convenience. You just want to move all the parameters a little bit to make sure the Jacobian with respect to the output layer is a full rank matrix, and then move the weights of the output layer a little bit to get the decrease. That's kind of what this is trying to say. Yeah.
Can you explain to me the gap between no spurious local minima and then earlier suggesting first order methods are actually finding second order?
Yeah, so
what's the gap there?
The gap is that, for example, if I had, imagine this was 10 layers. So I had A, W1 through W9. And then all of the W1 through W9 are in a rank degenerate configuration. Let's say they're all 0. Then I need to move every one of them a little bit to make sure the Jacobians are full rank. And then I move A a little bit. So that's like a 10th order decrease. So the amount of decrease I'll get is WL minus WL initial to the 10th power or something. And those SGD will never see. It'll only see it if it's a second order decrease. Okay, yeah, so essentially these two flavor theorems, they're quite similar, at least to me, is that they kind of say that if you have one layer that's wide enough, morally speaking, you shouldn't be trapped there. And the reason they're not quite constructive is, if you have this non-increasing path, but it's very flat, then a gradient algorithm will never see it. Yeah.
I'm curious, maybe you're going to discuss this, but how many orders does stochastic gradient descent see? Two, still?
Yeah. Oh, and it's trickier than that. Imagine if this activation were ReLU, you would think that's a second order decrease. But technically it won't go through because it's not smooth and things like that. And if you try to smooth it, then the decrease isn't second order anymore. Because then at 0, it'll look like a higher order thing. So there's no way to go around this, really. Okay. So this is also related to, so maybe in the early 90s, people looked a lot at what they called greedy algorithm, which is essentially Frank-Wolf for gradient boosting. And it also has this flavor of functional gradient descent. You want to go again in the direction of f minus y. Let's look at only the two-layer case. My weak classifier will be the single neuron. And then I'm going to boost it. I'm going to do functional gradient descent. So then I'm going to get some linear combination of these single neurons, which is obviously now a two-layer network. So at every step, what you want to try to find is a network that kind of a neuron that approximates f minus yi, right? Okay. Essentially, Frank-Wolf is basically gradient descent, except every step you're putting in a new neuron at 0, and then you're doing some local search on that parameter at 0 to try to find the decreased direction. So if you could find such a decreased direction, then Frank-Wolf converges at like some 1/k rate, because it's gradient descent on function space. So when can it make, the question really is, when can you find such a neuron using an efficient algorithm? So if adding the neuron makes first order progress, meaning it's positively correlated with f minus y, then gradient descent will see this. It's strictly positive correlated with the correct normalizations. So the angle is less than 90 or something. Okay, so otherwise you need to find a direction of higher order correlation. So if, for example, if a single neuron can't correlate with the descent direction, f minus y, then it's hard to find. The notable exceptions are when the correlation is second order, and again, you can write down a correct matrix to eigendecompose and solve this. This is done in a paper by Livni, Shalev-Schwartz, and Shamir, where they looked at quadratic activations. And they showed that when your activations are quadratic, you can implement Frank-Wolf efficiently, and it finds a global minimum. And if the activation is monomial, again, it's some sort of kth order tensor decomposition problem to try and do one Frank-Wolf step. Okay. What's next? Okay. So that kind of finishes my section on these sort of less algorithmic-y results. Any questions before I go on? How much time do I have? 10 minutes? Okay. Oh, yeah.
So can you now go back to the example you presented at the very beginning? You don't need to change, but just going back to the example you presented at the very beginning.
The experiment.
The experiment.
Yeah.
Can you now tell us how the theoretical results shed light onto explaining the phenomena?
I mean, they're all just suggestive, like I said. So all of the results I've covered so far say nothing quantitative about the activation was not quadratic. The only cases I talked about with quantitative results are single neuron or quadratic. And in fact, this is not understood. There's no result in the literature that says if my teacher network is k neurons with order k or k log k or even k squared, I can learn it. There's no result that says this in the literature.
What about the most recent one? I mean, the one that you had.
No, you need like super smooth. You need like, non-ReLU. You need like monomial low degree activations, right? Yeah. For those, you need low degree activations.
You get poly K also in this case.
Poly K for constant degree, roughly, or geometrically decaying things. Yeah.
But that results in the existence of a decreasing path from any initialization to the global minimum.
Yeah, it doesn't say anything.
That tolerates ReLUs.
It tolerates ReLUs, but you won't see it in the algorithm.
Why?
It's a higher order descent. It's if you can find. So let's put it this way: if you can solve a Frank-Wolf step with, basically what that requires to do is to solve Frank-Wolf. You need to find a neuron to add a ReLU to try and get decrease.
Yes.
Solving a Frank-Wolf step with a ReLU is equivalent to finding second order stationary and constrained optimization, which is a hard problem. It's copositivity. You need to compute like a negative eigenvalue subject to polyhedral constraints, basically. You want to solve like min AX greater than 0, X transpose HX. It basically requires you to solve things similar to this. So that's why I said everything so far is suggestive, really.
But what about the opposite direction of starting with over-parametrized and then reducing?
Sorry, what do you mean?
So that problem needs to be solved in order to add a new neuron.
To add a new neuron.
And that would be the case when you begin with an under-parametrized problem and you want to
Oh, you mean start with over-parametrized? Yes. The problem is you can't rule out when they all collapse and become degenerate. Like you start with infinitely many neurons and they collapse to a low measure set. If you can say that they stayed absolutely continuous and quantitatively, then yes, all of these are. Then yes, it's a global min. Right. Any other questions? Yes.
How about gradient-free methods? Why do you?
You mean zeroth order optimization?
Like evolution strategies, CMA.
I don't know what. I don't think they would.
Based methods.
I don't think they would guarantee anything. Although I don't know of any study of them either. So, at least recently. Yeah.
This may be trivial, but in all your formulation, I don't see bias terms. So does it matters on all the results, or it's also trivial to just evolve, like just add one in the X and?
That's an interesting question. I'm not actually sure. Some of these results are very sensitive. I think some might break with biases, I think a lot of them break with biases. Except the topological ones, I think. Those are probably fine. A lot of the quadratic activation might break.
Thank you.
Okay. Yeah. Yeah, let me just say what I'll talk about next time then. All right, so next time I will talk about results that are algorithmic. These results that allow you to locally linearize yet get the error to 0 or very small. And then I'll talk about why they're not quite a complete understanding yet, and contrast them to some work on these global dynamics, this Wasserstein viewpoint. And that's all for today.
I don't want to